All right, good evening, guys. So I'm going to realize a set of problem organization 2.1, and I'm going to start by working on the function on the problem number 11. So problem 11, and all of these problems start page 100. So on the problem 11, you got a function who looks like somewhere like that. And the question is find the domain. Remember that the domain is defined as all the value of x, and all the value of x are read on the x-axis. So how many value of x can you see? Well, when you look at this graph, every single point is defining a value of x. Every single point of your graph is defining a value of x. With these two arrows right here, that means your graphic is going toward infinity, meaning there is an infinity of points going up and an infinity of points going down. Therefore, my domain is being equal to negative infinity from negative infinity to plus infinity, and always a parenthesis for negative infinity and plus infinity. If I look at the problem number 11 now, problem number 13, what do I have? Is something that look like this, with this point right here being coordinate 0, 3. I got the value of y, and this is where I got the value of x. Well, the domain in that case is again all the value of x, and every single point that I can have on my graph will be defining the value of x. So every single point. There is an infinity of points going toward plus infinity on x, but I can see clearly that there is an open circle right here. And this open circle means that x equals 0, okay, is not part of my domain. Therefore, I'm going to define my domain as from 0 to plus infinity, with a parenthesis on plus infinity, but I'm going to express the fact that 0 is not part of my domain as a parenthesis corresponding to the open circle. Now, if I look at the problem number 18 now, on the problem number 18, we're having, again, a Cartesian system coordinate. We're having the point negative 1, 3 right here, and then we're having horizontal line, solid dot, going to plus infinity in terms of x and y. And so the question in this case is define the domain, define where it's increasing, where it's decreasing, where it's constant, define the domain in the range. So using what you're supposed to know to define where it's increasing and decreasing, we can clearly, when I look at my graph, reading my graph from the left to the right, define that from negative infinity to, actually I'm going to do that right here, from negative infinity to x equal negative 1, with a bracket for negative 1 because of the open circle, okay, because of this open circle, and always a parenthesis on my next to infinity. I will have my function who is decreasing. Then if I go from negative 1 to the second point, where x this time is equal to 4 and the y equal 3. So from negative 1 to 4, 4 and 1 and negative 1 included, my function is constant. Meaning that for any value of x, y will be the same. Then from x equal 4, with a bracket next to x equal 4, to x equal plus infinity, always a parenthesis next to plus infinity, my function is decreasing. is increasing, I'm sorry. If you really want to prove it, I would like to remind you that if you are defining 2 points and you have x1 is less than x2, well, to define that you have a decreasing, that means you are going to end up to f of x1 greater than f of x2. Now, on this one, well, f of x1, oh, that is not, wait, I need to change the tip of my pen. Okay, so f of x1 equal f of x2. And you will prove also in this case that if you have x1 less than x2, well, f of x1 is supposed to be less than f of x2, and that means your function is increasing. Now, if you want to look for the domain, so give me a second. So if I want to define the domain, well, my domain is going to be all the value of x, and there is an infinity value of x. There is no discontinuity, so it's going to be negative infinity to plus infinity. In terms of the range this time, I'm going to start from here, and y equals 3 when I am right here. So from 3 to plus infinity each time, I will have a bracket on for 3, as I am dealing with a solid dot, and I end up to have, that is my range. Okay. All right, so now let's focus on the problem I'm going to do problem number 39. So if I do the problem number 39 now, on the problem number 39, we are dealing with a graph who is looking like something like this, with the y-axis here, the x-axis right there, and the question is, using visual observation, determine whether each graph is symmetric with respect to the x-axis, y-axis, or the origin. So when I look at the x-axis, I just need to imagine that I'm flipping my top, if I call that the top of my Cartesian system coordinate, and that my bottom, and if I flip the top on my bottom with regarding the x-axis, I can clearly say that yes, x is an axis of symmetry. Yes, x is an axis of symmetry. Yes, x, axis of symmetry. Of symmetry. I can do exactly the same thing if now I'm taking this side and I'm flipping over this side. I will be able to say that yes, y is an axis of symmetry. Finally, I can clearly also see that if I take a point regarding the origin, I will have its symmetry, and so yes, and I'm going to use the blue, yes, O, origin, symmetry respect to the origin, symmetry respect to the origin. Okay? All right, so now let's try to do a problem like number 59. On the problem number 59, we are dealing with a function f of x equal to x to the fourth minus 7x squared plus 6. To define if a function is even, what you need to do is you take your function f of x and you're substituting x by negative x. And if you find that f of x equal f of negative x, that means your function f, the function, is even. So every single value of x will be every single x will be substituted by negative x. And now I got negative x to the fourth minus 7 times negative x squared plus 6. Because of the even exponent, I end up to have x to the fourth minus 7x squared plus 6. And I realize that f of negative x is exactly the same than f of x. In that case, f of x equal f of negative x. And that means that your function is even. Now, if I want to check that my function is odd, I'm going to do problem number 69. Let's do problem number 69. And if I do the problem number 69, first of all, my function f of x is 1 over 2x. So I'm going to have f of negative x, and I'm going to substitute x in my function f of x by, and I'm going to use another. So I'm going to use, there we go. So I'm going to calculate f of negative x, which is 1 over 2 times negative x, which give me minus 1 over 2x. And so negative 1 over 2x. And if I want it to be correct, first I should write 1 over negative 2x, which is exactly the same thing that negative 1 over 2x, which is minus f of x. Now I've got f of negative x equal minus f of x. That means my function, therefore the function is odd. So very simple to define if a function is odd or even. Let's do problem number 73. Last problem. So problem number 73, I'm going to problem number 73. The value of f of x, the expression of f of x is cubic root of x cubed minus 5x. And so if I'm calculating, oops, sorry for that, f of negative x, which is equal to the cubic root of negative x cube minus 5 times negative x, I end up to have cubic root of negative x cube plus 5x, which is equal to the cubic root of minus x cube minus 5x. Using the fact that square root of a multiplied by b equals square root of a multiplied by square root of b, I end up to have f of negative x equal the cubic root of negative 1 multiplied by x cubed minus 5x. There we go. Do that properly. And so I end up to have the cubic root of negative 1 multiplied by the cubic root of x cubed minus 5x. Cubic root of negative 1, it's negative 1. So negative 1 multiplied by the cubic root of x cubed minus 5x, which is equal to negative 1 multiplied by f of x. And so therefore I just proved that f of negative x equal minus f of x. And that means my function f, the function is odd. Alright, thank you guys, and I hope this set of problems will help you to improve yourself.